So after making mesh in the ICM CFD, and now we are going to solve the case in the Fluent. And for this case, the boundary conditions are Mach number 3. And the pressure on the inlet is a 101325. This is the atmospheric pressure at the sea level. And we assume the flow is inviscid, so we will be using the inviscid model. And in solution method, we will choose the implicit method. And other methods are the segregated solver. Just take a look on the workshop number 6 where I discuss about these solvers. So one of them, they rely on the pressure correction like that. But in the implicit solver, all the equations, momentum, continuity, and energy equation, they are solved in a single matrix in a one go. So it will require the more memory, but the solution will be speed up, and it will give you some very quite good results for the compressible flows. And the first time, normally, usually speaking, we use the simple methods, upwind, something like that. Not upwind, but this is the upwind is for the flow scheme. But for flux type, we normally use the row type flux. But for this case, it is recommended to use the AUSM type of the scheme. And in the flow scheme, we will go for second order upwind scheme, but that will be depends on your solution settings. So we will try to be on the side of the second order upwind scheme. And we initialize solution from inlet. And then we will use the solution steering with a supersonic type of flow. And the initial coordinate number we set is a 0.1, and up to 120 it can increase automatically. And for the first few iteration, solution is assumed to be zero order, means the first order scheme or 0% of the blending. And then I will gradually increase to the 80%. And I will run this case for maybe 1000 to 10,000 or maybe 1 lakh iteration depending on the current number of solution. If it's very low, then we have to run for more iterations. And if we can achieve the more value, the solution is stable and the mesh is good, then we can get a solution within maybe less than 1000 iterations. Now from the file menu, click on read and mesh file. And I will read the file which I saved earlier, 3-step wedge.msh file. And this file contains a 1.3 million nodes around, roughly speaking. And here the mesh file. And first thing I will do is that I will click on display. And from here I will uncheck the option for faces. This will not give you the solid type of the display. And from colors I can choose color by ID. So every surface or the volume has a separate ID, a unique ID. So based on this one also it will give you some colors. And also based on the type of the boundary. So for inlet, for example, the color of boundary is the blue. So I don't see it anywhere. So I want to check that the boundary condition is okay or not. So it's a pressure far field. And for pressure far field, we have the color as a light pink color or red color. And for outlet, we have the red color for sure. And for the walls, we have the white color. So these all are the walls, and they are they are slip condition because we are solving as an inviscid. And the next thing is that we have to check. Also, you can display the bottom here in this way. And if you choose the faces only, then the view will be like this. You can hide the, let's say, side one, maybe top in this way, and you can zoom the geometry to the wedge, and you can have the look on the geometry from inside of the domain. The next thing is that you have to check the mesh, and the negative volume should not be, the minimum volume should not be a negative volume. It can be zero. It can be a very low value, but it should not be zero value, or it should not be negative value. And then report quality. And I told you that the 0 is the worst quality and 1 is the best quality. And the minimum quality should not be less than the 0.01 for the minimum orthogonal quality metric. And for this case, aspect ratio is the 74, which is good enough. And the solver you choose is density based. So for any compressible flow, we'll go for density based solver. And especially for very high Mach numbers, you have to choose a density based solver and designed for these type of flows. Because the density is varying in this type of flow, so we have to use this method. In the models, I will not choose any double model. Instead, I will choose the inviscid here. And you can go for these double model, especially Spalding-Alvarez and the K omega SST. And you can do it and compare results with the results we are getting from inviscid solution. And the next thing is that I will be using in the material properties, it should be a ideal gas, and click on change create. It's very necessary to click on change create, and this will also enable the energy equation. This will turn on the energy equation from here. And now go to the boundary conditions, and at the inlet we put the Mach number as a 3. So first, the pressure at the inlet, as I told you, is 101,325 pascals. Mach number is 3, and the flow can go from the plus x to the, in this way, from minus x to the plus x. So from right to left side, from left to right side. So click on OK, and in the thermal, put the value of temperature of sea level, which is 288 kelvins, and at the outlet we have zero pressure here, so you can put the value as a 101,325, and put the acoustic wave as a non-reflecting, like this. So you can just turn off this value here. And meanwhile, you have to put the operating pressure, because operating pressure plus a gauge pressure will be equal to the atmospheric, the absolute pressure. So we can put the value 0 here, because I have already put this value atmospheric pressure into the inlet conditions or the outlet condition. So that's why we have to do it in this way for the compressible flows. And for other boundaries, there is a wall condition, and they are just have the wall. It's an inviscid wall. And second thing, I was telling you again and again that you should not be enabling the solid from the screen. So anyhow, in my previous case, the solid was enabled and it is just imported into the model. So you can delete them. So from setting on domain, you can go, and from here you can click on delete on the zones, and then choose the zone you want to delete. So I want to delete the zone inside the wedge, because there will be no flow inside the wedge is going there. All the flow will be going over the wedge. So just delete this one. So it has just deleted the solid domain from our model. And now write down the case file in the same folder. And now you can observe we have the only single cell zone condition here. And second thing you will observe here that we have the only one condition of our wedge. Otherwise, previously we had the wedge and the wedge shadow. And this is especially useful when we want to have the heat transfer analysis between the inside the domain of the wedge, which is solid domain, and outside, which is the fluid domain. So we want to have the heat transfer from or to the wedge. So in this case, we don't want to have any heat transfer, so we don't need any mesh inside this zone. And after that, I will be setting the reference conditions. This will be very helpful when I want to evaluate any non-dimensional quantities. And you can discuss about the area. Maybe this area may be the normal area on the outlet of this wedge, or maybe some formula for the area. You can find out from the internet how people use for this type of case. And in the methods, it's implicit. And from the row FDS, I will use the AUSM as I told you earlier. And the flow scheme will be second order upward scheme, but I will control this one from the run calculation. And the controls don't do anything to the current number. This will be also controlled by solver from run calculations. So just directly go to the initialization, and this time I will use the initialization from inlet. So it will have the x velocity only, no y velocity, no z velocity. Initialize. And also change the monitor properties for residuals. So just put some zeros so that it should not converge too early. So maybe like this. So I will put the, let's say, minus 18. Okay. And then in the run calculations, let's say number of iterations are 10,000. So that I can run case for infinite number of iterations or maybe very long number of iterations. And this will give me the freedom to stop solution when I want to stop the solution. And then click on the solution steering. And this is very handy for the solution we are undertaking, which is the supersonic flow, and the flow is compressible. And the type of flow here is supersonic. You can have the subsonic, incompressible, transonic, supersonic, hypersonic. So for our case, this is a supersonic flow. And initially I will keep the blending between the first order and second order scheme to the 0. So means that we are now solving the first order upwind scheme. And when we slide this one towards the here, so basically now we are solving the second order upwind scheme. So for initial settings, just put the value as a 0. And from settings, put the initial coordinate number as a 0.1. And update coordinate number immediately. So it will not wait for the 100 more iterations. And depending on solution, it will change the coordinate number from 0.1 to the 2000 to the 200. And if solution is converging smoothly, this will increase the number of the coordinate number to the higher value. And if there is any problem in solution, this will reduce the coordinate number to the minimum value is the 0.1. Okay. And now click on calculate. And this will just create the grid levels for the FMG initialization. So after creating the 4 to 5 levels, it will continue with the solution iterations. And now you can see that I've just stopped the solution after the just one iteration. So I just want to show you that how it works. So full multi-grid initialization, or FMG, it took the levels, different levels, and there are the 5 levels, 0 to the 5. And after initializing solution with the FMG, now we will continue with the solution and click on continue. So this will continue solution, and after 30 or 40 iterations, I will change the scheme from 0% to the maybe 20%. Slowly I will increase up to the 80%. Okay, so solution has been run for the 1045 iterations, and I just fall asleep. And after waking up, I have seen that the number of iterations are now 1045. And typically speaking, I will be changing the scheme from 0% to the 20%, 30% after the 100 iterations, or maybe I will wait for the 30 more iterations. So that because after 100 iterations, it will change the coordinate number after the interval of 30 iterations, and after 30 iterations, the Fluent will check the solution convergence type at the level. And the coordinate number has been increased from 0.1 to the 8.04 automatically by the Fluent, and that depends on the solution convergence level. So if the solution is converging very smoothly, then it will increase the coordinate number steadily after every 30 iterations, and there's some problem in the solution, this will decrease the coordinate number to some optimum value where solution will not diverge, but rather it will be continuously converged to the some lower values. And from here I will change the scheme to the 40% of the second order, and this is the blending between the first order and second order scheme. So right now we have the 40% of the second order blending, means that the 40% is second order and 60% is the first order. And now again click on the calculate. And you can see the spike in the convergence plots, the residual plots of the momentum and other equations. And this is very normal when we change any parameter in the solution. And after some time, this will converge to the some again lower values, and might be the corner number increases to some higher values. So I will just run this solution for maybe more than 100 iterations more, and then I will see that how it is converging, and then I will increase the value to the 80% in a one go. But if you get the problem, then you can increase this value in the interval of 10 or 20% after the maybe 100 iterations. Okay, so here I stop the solution after 1540 iterations, and if you run this case for maybe more than 2000 iterations, the corner number may reduce to the lower value, to the higher value. And in the next video, I will show you that how you can post-process the results. And one more important thing is I want to discuss here is that how you can auto-save the solution after some iterations. So let's say if I save the data file every maybe 100 iterations and retain only the some number of files, so it will not save the unlimited files on your hard disk, and in that case your hard disk may run out of space. So let's say we put the number of case files 20 and save associated case files only if modified or each time. For transient cases you will save them each time, but for the steady state cases you will only save with if they are modified in case of boundary condition or some settings, like for example we change the settings from the 0% of the first to higher order blending to the 80%. In that case the case file is changing, so this will save the case file after any change in any one of the parameters in the case file. And also you have to delete the file name from here. It will automatically take the file name from the where it is saving the file already there. So always you have to either browse the file name and the folder, or just delete the file name from here, or you want to save in some other folder where you want to save it, so it will not save in the working directory like right now you are working in, and you want to save some other location, then you can do it also, and you have to click on the browse. In the next videos I will discuss about the post-processing of these results in the Fluent, and then also in the text plot, and then in the AutoCAD as well for measuring the angles of the